In today's video, we'll be taking a look at exponential growth and decay, as well as some other exponential models. And so we're going to see three different types of models. Exponential growth and decay counts as one model. We will then look at a learning curve as well as the logistic growth model, and then we will be solving problems that involve these types of exponential models. To get started, let's consider the function given by q of t equals q naught e to the k times t. Q naught and k are both constants, such that q naught is equal to q of 0. So we call this the initial value. Right, so q of t is a function that represents a quantity at a time t. Now, let's take a look at the derivative of q of t. This will give us the derivative of q naught e to the kt. Right, using the constant law, or the constant multiple law rather, this is q naught times the derivative of just e to the kt. And now we can use a chain rule to say this is q naught k e to the kt. If we rearrange our terms a little bit, we can write k times q naught e to the kt. But this term right here is q of t, so this is just k times q of t. Now, q naught must be greater than 0. It's representing a quantity, and a negative quantity doesn't make sense. So this would mean that q of t itself would be greater than 0 for every value of t, right? Because e is also always positive. So we have a positive value times a positive value. Thus, we get two conclusions from this analysis. If k is greater than 0, then q prime of t is greater than 0, which means that q of t is increasing. In this case, this is known as exponential growth. We call k the growth factor. Now, if instead k is less than 0, then q prime of t will be less than 0 for every value of t. This means that q of t is decreasing. This is an exponential decay. And in this case, the absolute value of k, since k is negative, is called the decay factor. Right? So this function right up here is our exponential model. If k is greater than 0, it is called an exponential growth. If k is less than 0, then it is called an exponential decay. Next, we examine the function Q of t equals c minus a e to the negative kt, where c, a, and k are all positive constants. Now, Q of 0 gives us c minus a. Q prime of t would be a k e to the negative kt. This will always be greater than 0. Okay? And so this means that Q of t is increasing. So we have an initial value of c minus a. We also know that Q is strictly increasing. Now let's examine end behavior. So if we let the time go to infinity for Q of t, then what we have is this limit right here. Using the laws of limits, we can write this as the limit of c minus a times the limit e to the negative kt. However, this limit will go to 0. So what we're actually left with is c. This says that this growth is going to start out rapidly, but it will begin to slow down, right? Again, we can see this if we take the limit as t approaches infinity, q prime of t. We would get ak, because they're constants, limit as t goes to infinity, e to the negative kt, which is just 0. So the rate at which this function grows is slowing down, and it's leveling out to c. Now, this behavior resembles the learning pattern experienced by workers engaged in highly repetitive work. For that reason, we call this function right here, this Q of t, the learning curve. Finally, let's examine the function. Q of t equals a over 1 plus be to the negative kt, where a, b, and k are positive constants. Now we call this logistic growth. Now let's notice something. First, let's take a look at the limit as t approaches infinity of Q of t. Right, this will be the limit as t approaches infinity, a over 1 plus be to the negative kt. This term will go to 0 as t goes to infinity, so we're left with a over 1, which is just a. So in the long run, this function will equal a. Well, let's take a look at its derivative. Right, the derivative would be negative a over 1 plus be to the negative kt squared. That is the power rule. Then chain rule, we have to multiply by a negative bk e to the negative kt. So this will simplify out to a bk e to the negative kt all over 1 plus be to the negative kt squared. Since a, b, and k are all positive constants, and since the exponential function is always positive. This derivative is greater than 0, which means, right, that q of t is increasing. Specifically, it's increasing up to the value a, right? Because a is the maximum value we can have based on this limit up here. Let's take a look at the limit as t approaches infinity of q prime of t. Right? Now this e to the kt, negative kt rather, will go to 0, as will this one down here. We're left with 0 over 1. Right? So this limit is 0, which means that the rate of growth is decreasing. A more in-depth analysis will show that the rate of this decrease is actually pretty quick. So what this is saying is that this logistic growth function exhibits properties from both of the previous functions we've analyzed, exponential growth as well as learning curve. It exhibits the property of rapid growth of the exponential growth, because this function will begin increasing rapidly, but then this growth will begin to decrease. So it also exhibits the saturation property of the learning curve, in the sense that it's leveling out to a specific value. Let's close out this video by looking at several examples. Right. Start with this here. Under ideal laboratory conditions, the number of bacteria in a culture grows in accordance with the exponential growth law. That is the law q of t equals q naught e to the kt, where where t measures the elapsed time in hours. Suppose that 10,000 bacteria are present initially in the culture, and 60,000 are present 2 hours later. How many bacteria will be in the culture at the end of 4 hours? And then how quickly is the bacteria increasing at this point? Right, now we know that Q naught is 10,000, so we can start with Q of t is equal to 10,000 e to the negative kt. We need to find the value of k. We need to find the growth rate, what is it called? The growth constant. Well, we know that after 2 hours, so Q of 2, which equals 10,000 e to the negative 2k, this value is 60,000. So we can now use this to solve for k. This would mean that e to the negative 2k is equal to 6. Right? Why did I do negative? I'm sorry. It shouldn't have been negative kt. It should just be positive kt, right? This would mean that 2k is equal to the natural log of 6, right? Or that k itself is equal to the natural log of 6 over 2, which can also be represented as the natural log of the square root of 6. Therefore, our model, Q of t, is 10,000 e to the t times log of root 6. So for this particular problem, our exponential growth model is right there. We can now answer the question after 4 hours. So we want Q of 4, 10,000, e to the 4 log of root 6, which is 10,000, e to the log of 36, which is just 10,000 times 36, which is 360,000. So after 4 hours, there are 360,000 bacteria. We also want rate of growth. So we want Q prime of 4. Right, this is the derivative of 10,000 e to the negative t log root 6, evaluated when t is equal to 4. And so we get negative 10,000 log of root 6. Again, I don't know why I keep putting negatives. So it's just 10,000 log of root 6 e to the t times log of root 6 evaluated when t is equal to 4. Right, which is 10,000 log root 6 e to the 4 log root 6. Now 10,000 e to the 4 log root 6 was 360,000. So that's now times log of root 6. If we approximate this, and of course we want to keep it to the nearest whole number since we're dealing with number of bacteria, we find is about 322,517 per hour. Right? What this means is that right at 4 hours, approximately 322,517 more bacteria will appear in the next hour. Right, now for our next example. So radioactive substances decay exponentially. The half-life of a radioactive substance is the time that is required for a given amount to be reduced by 1/2. Carbon-14 is a radioactive isotope of carbon with a half-life of 5,730 years. We are asked to determine its decay constant. Right? So we know that Q of t is Q naught e to the kt. We also know that Q of 5,730 will equal Q naught e to the 5730k, and this is Q naught over 2, right? It's the initial amount divided by 2. So what this means is that e to the 5730k is equal to 1/2. So 5730k is equal to the natural log of 1/2, which is also negative natural log of 2. Therefore, our decay constant k is negative log 2 over 5,730, which is approximately 0.00000121. So for carbon-14, when dealing with half-life, this is our decay constant. Okay, next, a skull from an archaeological site has 1/10 the amount of carbon-14 that it originally contained. Determine the approximate age of the skull. Now, remember, our model, Q of t, is Q naught E to the negative log 2 over 5730 times t. Right, we found the decay constant in the previous example. We want to set this equal to 1/10 the original amount, so Q naught over 10, and solve for t. This will give us an approximate age. Well, this would mean that e to the negative log 2 over 5730 t is equal to 1/10, which means negative log 2 over 5730 t is equal to log of 1/10, which is negative log of 10. Right? T log 2 is equal to 5730 log 10, which means that t is 5730 log of 10 divided by log of 2, which turns out to be approximately 19,034 years old. So this skull is about 19,304 years old. Now, let's take a look here. Camera division of Eastman Optical produces a 35mm single lens reflex camera. Eastman's training department determines that after completing the basic training program, a new, previously inexperienced employee will be able to assemble that function Model F cameras per day T months after the employee starts work on the assembly line. So this Q of T is a learning curve. How many Model F cameras can a new employee assemble per day after basic training? With 1 month experience, 2 months experience, 6 months experience. And then how many Model F cameras can the average experienced employee ultimately be expected to assemble per day? Right, well, there's really not much to do here. Right, so new employee. Would have 0 months of experience, so it's Q of 0. Right, that is 50 minus 30, which is 20 per day. So 20 cameras per day. So that's for a fresh, inexperienced employee. Now, after 1 month experience, now T is 1, so we're looking at Q of 1. This is 50 minus 30 e to negative 0.5, negative 1/2. This is approximately 31 cameras per day. Two months experience. And we're now looking at Q of 2, which is 50 minus 30 e to the negative 1. And this is about 38. cameras per day. Let's now jump to 6 months experience. That's 50 minus 30e to the negative 3. And this will be about 48 cameras per day. Now we want in the long run. Well, that is the limit as t approaches infinity of q of t. And in our analysis I saw that was going to be a, which is 50 cameras per day. All right, so it's expected that the average experienced employee will be producing 50 cameras per day. And one last example. So the number of soldiers at Fort MacArthur who contracted influenza after T days during a flu epidemic is approximated by the logistic growth model given. If 40 soldiers contracted the flu by day 7, we wish to find how many soldiers contracted the flu by day 15, and also how quickly the rate of infection is increasing. Now, Q of 7 is 5,000 divided by 1 plus 1249 e to the negative 7k, and we know that this is equal to 40, so we just have to solve for k. Right, 5,000 would equal 40 times 1 plus 1249 e to the negative 7k. 5,000 over 40 would equal 1 plus 1249 e to the negative 7k. So 5,000 over 40 is 125. So 125 minus 1 now is that 1249 e to the negative 7k, which means that 124 divided by 1249 is e to the negative 7k. Right? Negative 7k would then equal the log of 124 over 1249. Right? So k itself is negative log 124 over 1249 all over 7. Right, therefore, our model is given by q of t, which equals 5,000 over 1 plus 1249 e to the negative log 124. What I'm going to do is simplify this. I'm going to use this notation here. Exp of x is the exponential function e to the x. And write exp of negative log 124 over 1249 divided by 7 all times t. We were asked 15 days. So q of 15, 5,000 divided by 1 plus 1249 exp, so e to the negative log of 124 divided by 1249 divided by 7, then times 15. And plugging this into a calculator, we find approximately 508 soldiers have been infected after 15 days. We now want Q prime of 15. Right? So this will be 5,000 times the derivative of 1 over 1 plus 1249 exp of negative log 124 over 1249 over 7 times t, evaluated when t is equal to 15. This derivative negative 5,000 times 1249 e to that then times the natural log of 124 over 1249 divided by 7, and this whole thing is over 1 plus 1249 e to the negative log 124 over 1249 over 7 times t squared. Now, we just have to evaluate this at t equals 15. Right, plugging that in to a calculator, we find it's about 150 soldiers per day. So after the 15th day, the flu is spreading to an additional 150 soldiers per day. And that concludes this video on exponential growth and decay, learning curve, and logistic growth models. In the next video in the series, we'll be looking at optimization problems, which also happens to be the final video on applications of the derivative. So I will see you all in the next video.